Okay, so this is the typical stoichiometry problem. It's going to be in 4 parts. And I mentioned this before. Let's see, let me turn off the lights. Okay, so if there's a chemical reaction versus a physical reaction, like a chemical reaction where things chemically change, you need to balance the equation. Next thing is what is given. Sound familiar, right? Number 3, what to calculate. And lastly is the setup. Okay, so let's look at a typical, very simple stoichiometric problem. Okay, when methane burns in oxygen, water and carbon dioxide are produced. So if we have 13 grams of methane, how much? Need to finish. Oh, yeah, okay. All right, so how much water is produced if we burn 13 grams of methane? Okay, so first of all, whenever you have a chemical reaction, you've got to have the actual reaction there, because the first step is to balance it. So what is that? Okay. Okay, methane is CH4. Oxygen gas. Remember, there are 2 arrows there. Okay, so step 1 is balance the equation. Okay, is this balanced? No. And balance it really fast. Okay, so it's balanced. All right. So whatever's given, again, is going to go on the left. Oops, 13 grams. And we're trying to calculate grams of water. Now, the past dimensional analysis problems we've done, there's been no chemical reaction. There's only been a physical reaction or physical change. So now we have to go from grams to moles of methane, and then from moles of methane to moles of water, and then grams of water. So it's going to be in 3 parts. Okay, so molar mass of methane is, what's it, 1201, 60, 1605 grams. Right, that gives us moles of methane. Now we need to go from moles of methane to moles of water. That's the middle step here. So this is molar mass. We want to go from given to calculated. And a CH4 has got to cancel. We want to, and this is via the periodic table. Okay, and your balanced equation, actually this, and this is why we balance the equation for this middle step here. So you need to look at the ratio, the coefficient ratios of water and methane. So water is 2, methane is 1. That means for every mole of methane that's burned, you're going to end up with 2 moles of water. Okay, now we need to go from moles of water to grams of water, which is again the molar mass of water, which is going to be so everything cancels except for grams of water. What are we trying to calculate? Grams of water. So now we have 90% credit of that problem. Excuse me. 10% is over here. So we need to get a numeric answer. So we're looking at 3 sig figs, 4 sig figs. How many sig figs are in the middle there? 2 HOs over 1 methane. What does that mean? Correct. Perfect. That's infinite precision. Infinite sig figs. Because it's exactly 2 and exactly 1. We made it that way. Nothing's being measured here. So that ratio is not going to contribute to the sig figs of the problem. And here's 4 sig figs over here. So our answer is going to have 3 sig figs. Okay, so your answer needs to have the numeric part, the units, and correct number of sig figs. That's for 10%. So if this problem's worth 10 points, there'd be 9 points, 1 point. Now in your tests next week, you're going to have a number of stoichiometry problems. I want you to go through and set everything up first in case you run out of time. You can get a whole bunch of points just by a proper setup. Then come back afterwards and do them. Would be the way I would suggest doing it. That way you'll maximize your points. Okay, so 99% of your simple stoichiometry problems are going to look like this. I'm going to have what you're given, you need to convert to moles. Do a mole-mole relationship from the balanced equation. And then we're going to convert the moles of what we're trying to convert to back to whatever the units the problem asks for. So for example, in the case of gaseous liters, that is at standard temperature and pressure, this is not going to be grams per mole, it's going to be liters per mole. Or say if you start with 4 times 10 to the 23rd molecules of methane. So this is going to be Avogadro's number here instead of the molar mass. You just got to get it to moles. And then this relationship from the balanced equation is a mole to mole relationship. Remember, there are 2 things from a balanced equation, molar relationship and molecular relationships. So we can't do anything until we get to moles. Yeah. Yeah. Just like that. Okay, so are there any questions about this guy? Does anyone suffer from migraines? Yeah. It's from the why? Yeah, yeah, exactly. Because it comes directly from the balanced equation. And this is why we balance the equation. Otherwise, what's the point, right? Oh, anyway, does anyone here have migraines? I'm surprised. I think I'm starting to have migraines. My neck will feel like I've been lifting the world with it. And then my eyes become super sensitive to light. I mean, it's like it's blinding white light. I've been reading up on migraines, and those are dull pain, sensitivity to light. And those are definitely what I'm doing. Like yesterday in lab, the end of lab yesterday, I was starting to feel weird. And it's fortunately I have sunglasses in my car because I couldn't drive otherwise. Almost everything is white. Weird. And I've never had migraines in my entire life, but got to start sometime, I guess. Okay, so let's do. Of course, the stupid cough doesn't help matters. Okay, so is everyone okay with this? What we've done so far? Theoretically, this should be a review for you. Let's do one involving, let's do the same problem, only using liters. Okay, so how much is grams? So we want how many grams of water is produced if 13 liters of methane is burned? Okay, so it's going to be the same equation. So we're going to use the same balanced equation right here. And given it's going to be 13 liters. And it helps to put the chemical above a given quantity, just to keep everything straight. Okay, so we need to get liters, and this is at STP. Okay, so step one is to get what you're given to moles. This is gaseous liter at STP. It's 22.4 liters per mole. That gets us moles of methane. We convert the moles of methane to moles of water in the middle step here. Then we need to go from moles of water to grams of water. Okay, does everyone see where I got everything there? So it's going to be 3 sig figs, 3 sig figs, infinite sig figs, 4 sig figs, 3 sig figs. Don't forget about your there are three main conversion factors we've been using. Avogadro's number, the 602 times 10 to the 23rd, 22.4 liters of any gas per mole, and then the molar mass from the periodic table. Those are the three conversion factors. Okay, so is everyone okay with this problem? Okay, so let's modify it yet again here. Okay, so how much carbon dioxide is produced if we burn 13 times 10 to the 20th molecules of methane? Okay, so I use railroad tracks all the time. You can use parentheses if you want. If you've learned from a past chemistry class where you're using parentheses, that's fine too, doesn't matter. For me, it's just less strokes. Okay, so step one is, this is the given, 1.30 times 10 to the 20th numbers of molecules. First step is to convert the number of molecules to moles. Okay, the next step is from the balanced equation. So we want carbon dioxide and methane. That's going to be 1 and 1, I believe. Yeah, 1 and 1. Now, 1 and 1 doesn't change the numeric value of your answer. But what it does do is make sure your units come out, because your units have to come out to be CO2. So if you don't include that, even though it's 1 over 1, your units won't cancel and you won't have carbon dioxide as a unit ending up. You're going to be ending up having methane as a unit. So make sure you have that middle step in there, even if it's 1 over 1. Okay, so our methane cancels, molecules cancel, moles cancel, leaves us with grams of carbon dioxide. And this is 3. Okay, we're looking at 3 sig figs, 3 sig figs, infinite sig figs, 4 sig figs. Our answer is going to have 3 sig figs in it. Okay. Is everyone okay with these 3 problems I did? Have any questions? Over here, it's 1.30, 3 sig figs, 3 sig figs, 602, infinite, and then 4 sig figs. So your answer is going to have the lowest number, which is 3. 99.999% of the time, yes. When you're adding, subtracting, it's different because you're just looking at the number of decimal places. But when you're multiplying and dividing, exponentiation, you just look at all the numbers, and your answer is going to have ones that are the smallest number of significant figures. In this case, it's 3. Okay, so this is a very simplistic problem. Now, the best way to word this problem is a little different than the way I have it worded here. Now, they need to use the word excess. Excess. So if I specify methane here, I need to say excess oxygen. Excess oxygen gas. Because excess oxygen gas means it's not going to come into the calculation. But what if we limited the amount of oxygen we had? So let's do a problem like that. Now, before I do another problem, does anyone have an issue with what I just done? Because the next step is going to be ugly. Yeah.
Isn't it 6.023 times 10 to the 20?
Yeah, it depends on how much. I usually go 602. And the reason why I go 602 is I'm a slide rule guy.
Okay.
And slide rules are 3 significant figures. So I always think in my head 3 sig figs. But it goes out. It's like pi, you know, those giant numbers. So so in my class, you can use 602 or 6022. A lot of times people use or 203. Does anyone know how to use a slide rule? Fewer people. When I watched the movie Apollo 13, there's a whole room of engineers. There must be 40 engineers there, and they're all using a slide rule. And guess what we did? We made it to the moon on 3 significant figures. Slide rule, pretty cool. Okay, all right, so let's now do the next step. Say again? I was part of the teacher program. You know, the one that blew up?
Oh, no.
Yeah, and yeah, I went through a couple levels of interviews, and then, you know, I didn't make the cut after that. But I was going like, when that thing blew up, I went, holy shit. My wife and I were looking at each other going, oh my God. Yeah, so really something. There's a TV series on, let's see, I think it's on Apple TV. I've been watching. It takes place when the Russians made it to the moon first. And it's really kind of cool. And then so the United States is playing catch up, and they do a lot of stuff, and it's some shoot up bang bang stuff, and it's really cool. I've really been enjoying it. It's in fact, it's on season 2 now. Now they're season 2 is off to Mars. Okay. Okay, so we're going to modify this. How much water is produced? 13 grams of methane is burned in a, let's say, 15 grams Okay, so we have 13 grams of methane, 15 grams of oxygen. How much water do you produce? So what's the given here? That's one given. Yeah. Yeah, we've got two givens. Two givens. Now this is going to complicate things a lot. Now, let me give you a simpler situation than this. I've got 10 bicycle wheels and 10 frames. Two givens, right? How many bicycles can I make? 10 wheels, 10 frames. So what limits the number of bicycles I make? Wheels or frames? Wheels. Because there are not enough wheels to go around with 10 frames. So the first step is, in your mind, you're saying, well, how many wheels go on a bicycle? How many frames go on a bicycle? If I had so many wheels on a bicycle, how many frames would that take? If I had so many frames, how many wheels would it take? So you need to do two calculations right now to determine what limits the number of bicycles. In this case, which one of these, oxygen or methane, will limit the amount of water produced? So that is two calculations, just like we've been doing. So we start with one, doesn't matter which one, see how much water we make. We do the other one, see how much water we make. And then whatever makes the least amount of water limits the reaction. Hence, this is called a limiting reactant limiting reactant. Sometimes they call it limiting reagent. So whenever there's more than one given, you're going to have to do 3 more calculations over and above a simple one. So you're going to end up with 4 calculations per problem. All right, so let's just start with 13 grams of methane. We want to see how much water we can make. Okay, so first step is convert grams of methane to moles of methane. And methane was 1605. Next, we need water, methane. That was 2 to 1. And over here we need it. So what we're doing now is methane cancels, grams cancel, moles cancel, and water is 1802 grams. Okay, so this will give us the amount of water if we just start with 13 grams of methane. Regardless, we're not listing the oxygen at all now. Okay, so that's the same calculation we did before. I'm glad I got the same answer. Okay, the next thing we're going to do now is use the other given. This is 15 grams of oxygen gas. Okay, so we end up with 29 grams, 8 grams. So it looks like the oxygen gas is limiting the amount of water produced. Okay, so you always have to do, if there are 2 givens, you have to do 2 calculations to determine what's limiting the reaction. If there are 3 givens, 3 reactions. Okay, so now we have methane left over because we didn't use it all. We used up all the oxygen. Methane's left over. So how much methane is left over? That's 2 more calculations. So we're going to start with our 15 grams of oxygen. And now we're going to see how much methane is used. That means we're looking for grams of methane. So this can be the same setup. And methane was 44, wasn't it? Yeah, 4401. And now this calculation will tell us how much methane is used. Of the 29, how much are we going to use? You know, how much of the 13 we're going to use? Okay. So the 13 grams, we're only going to use 10.3 grams. That means we have an excess. So if we start with 13 grams, we use up 10.3, we're going to have 2.7 grams excess. Yeah, it's the molar mass of methane. No, excuse me, that's carbon dioxide. See what happens when you try to remember? So it's 1201, 40, it's going to be 1605. Okay, so we started with 13 grams of methane. And we're going to use up 376. What is it? 24. So we're going to have 9.24 grams left over or excess. So that's the 4 calculations you have to make. So 3 of them are kind of stoichiometry problems, and the last one is a simple subtraction. Okay. Everyone okay with this? It's a pain, but yeah.
Can you explain the last Stoichiometry part of that, the third one?
Okay. The question is, explain the third one. Why do we need the third one there? Okay, we know that we used up all the oxygen, okay? Because the oxygen is what limits the reaction. That means it's totally consumed. But like with the 10 frames, building 5 bicycles, you have 5 frames left over. And how do you know how many frames you've used? That's the third step. How much of the one in excess is used?
So you use your limited reactant as your
Starting.
and then you use
And then
your
the other one, for which one to end up with? The one in excess. And the deal is how much of that do we use? So we know we didn't use it all.
Yes, so that conversion factor is the other reactant.
Yeah.
So I guess it's just
And then we know how much we've used by that calculation. Then we subtract that from what you started with. Better? Okay, so this needs practice, and I've given you lots of practice. If you go over to okay, so this is a whole bunch of worksheets. And the ones that say limiting reactant or limiting reagent is going to be like the one I just did. So on your test, you're going to have one limiting reactant problem, one simple reactant problem, some naming, going from formula to name to formula, and some dimensional analysis problems, and a take-home problem. Okay. Now the take-home problem is going to be multi-step. And over the years, I've been collecting these. I'll be in the shower and all of a sudden I go, oh, that's a good idea. And assuming I remember it once I get out of the shower, I came up with all these problems. Let me give you an example of one. Flying from Seattle to LA is 2.5 hour flight. A 737 burns, oh, I forgot what it was, 18.8 pounds of fuel per second. The flight takes 2.5 hours. Assume the flight is immediately to altitude and then immediately lands. How much ice is produced by that plane? So you need to know things like fuel flow. You have to know what jet fuel is, which is basically kerosene. And then you're just going to grind that out. A bunch of conversion factors and a stoichiometry problem because you need to know the chemical reaction for kerosene and oxygen. So that's a typical take-home problem. It isn't just a grind out deal. It requires some thought. Okay. I can show you what that problem looks like. Let's see here. Well, I guess I didn't bring my hard drive with me. I'm going to post that on here on the miscellaneous, just to give you an idea of and the answer, what a multi-step problem looks like. Okay, but that's for take home. And I'll post that sooner than later. Okay, your test is on Tuesday of next week or Wednesday? Tuesday. Okay, so I'll have it up. Someone gets to send me an email again. You're good at send me an email. Remind me to post the take-home problem. And I'll have it up tonight. We have lots of time. Okay, so what I'd like to do now is we have a little over half an hour left. Why don't I post a couple of problems up here and you guys can practice here? Okay, so why don't you guys go ahead and try this on your own? Yeah,
Can we go over the matrix calculator as well?
yes, I'm gonna let everyone do this. Okay, so basically right now I want you to find out how many water molecules are produced when you have 13 and 15 givens. So just go ahead and work that out. And the good news is you can work in groups if you want, together, that's fine. And I'd like for you to try this now while I'm here. I can answer any questions, okay? Okay. All right, you're going to be using, first of all, you need to have an equation.
Oh, I'm sorry. I was just writing down that.
Oh, all right.
But if you wanna- I wasn't sure what type of example we were using it for. We talked about it yesterday in class. So like this one, like the subscripts and the coefficient, and you said the matrix and the calculation. Because I have ADHD, so like taking like charge of numbers is kind of a lot if I don't have like a simple way to like visualize it.
It's kind of weird. Basically, we're going to assign each atom as a variable.
Okay.
Then you look at the relationship between the numbers of the atoms per molecule.
Like the number of atoms.
Yeah. Okay. And then you need to have, if we have 4 atoms, you have to have 4 equations because it's 4 variables, right?
Mhm.
Okay. Have you had any matrix stuff at all?
In calculus, but that was a while ago.
Okay. So you know about systems of equations, right?
Yeah.
Okay. Well, there's a way in matrix algebra where you can solve a system of equations using something called reduced row echelon format, RREF. Yeah, and so we're going to set up the matrix and do RREF on it.
Okay.
And then it'll give us the solution, which are the coefficients.
Okay.
Okay, so that's globally what we're going to do. That makes sense?
Yeah.
Okay. All right. So let's start with an equation. Let's do the methane burning.
Okay, so CH4. I missed part of
I
that.
can just tell you what it is.
Oh, okay. CH4.
Plus O2 equals arrow, water and carbon dioxide. Okay. All right. So how many variables do we have?
We just kind of each of these.
Yeah.
Or,
Atoms.
Four atoms.
Three.
Three.
Three different kinds of atoms: carbon, oxygen, hydrogen, right?
Oh, that's what you're saying. So you can see it, please.
Okay. Pretty good, huh?
Yeah, nice. I tried that as well.
Here, let me do this. Would have been opacity. Okay, so we have three atoms. Okay, and how many molecules do we have in the equation? We have 1, 2, 3, 4. So this is going to be a 3 by 4 matrix.
So then when you're setting it up,
Okay, so we're going to have carbon. Oops. CHO. Okay, so as we're going to go across here, how many C's are in this?
2.
One.
Or just this one right here.
Mhm.
We're not going
No,
to
we're going to do each one individually.
Okay.
So it's 1, right?
Mhm.
How many C's here?
0. 0. 1.
How many H's do we have here?
We're looking at the, okay. So
4,
0.
0, 2, 0. And O's, we have 0, 2, 1, 2. 3 by 4.
Gotcha.
Okay, so next we're going to do is going to go to matrix, which is a shift. Okay, and you can name them here if you want. I never name, it's A. Okay, and now we're going to edit the matrix. Okay, and we want a 3 by 4. I'm going to put these in. I'm going to go 1, 0, 0, 1. That's going to be 4, 0, 2, 0.
0, 2, 1, 2.
0, 2, 1, 2. Right? Okay. All right. Now we're going to go back to matrix. And we're going to do math on the matrix now. And that's where the RREF is. Okay. And which matrix are we going to do the math on? I'm going to do it on the first one. We need to finish out the parentheses. Enter. Quit. Why does it say that now? Here, if we take that. Oh, why is it doing an error? Need a type.
And they were specific on what they're actually.
Okay, button. Now, we want this one. Oh, good. I don't know why.
I think it has to be like on the main screen.
Okay, so this is the solution. Okay, so you've got, now notice there's a diagonal that's the same here. 1, 1, 1, 1.
Yeah.
So you've got 1, 2, 3, 4 coefficients. 1, 2, 3, 4. Okay. So we're just going to go in order that we put them in. So this is going to be 1, 2. -2 means it's across the equal sign. So it's going to be 2. And the diagonal is 1.
Wait. So you're not going across
Oh, the diagonal. See the 1, 1, 1?
for this one?
Yeah, that's the 1, 1. The diagonal is the last one.
Okay. And then for how'd you get this to? Is that
Now you
just-
start here on the top right and go down. 1, 2, 2, 1.
Oh, I see what you're saying.
Now sometimes you end up with fractions. You got to clear the fractions.
Mhm.
And you just want everything as an integer. So your diagonal is going to be, could be something else.
Yeah.
Now you have to do a bunch of these to remember all the steps. I mean,
I'll practice.
but it, and the deal I put on the miscellaneous files
Mhm.
will go through these steps as well. The equation's a little more complicated than this one.
Mhm.
This one I did because I just remembered it, which we just did on the board. So the time it takes is putting this in the calculator. And the rest of it is like, and the RREF solves simultaneous equations.
Mm.
And you get this plus 1, which is the diagonal. So if this is 5, they'll end with 6. 5 plus 1.
Oh, I see what it is now. Okay. Because it's like this one, and then diagonally 2, and then because of the -2.
Yeah, so you go to the far right. 1, 2, 2, 1.
Okay.
Let's see, where is that? 1, 2, 2, 1.
Thank you.
But when I learned this, I just forced myself, every time I had a balanced equation, I did it this way.
That's right.
Because I mean, this you can just look at it and balance it.
Yeah. So it's kind of just like when it's like the example that we had yesterday. I think it was like this one. Would that work?
Any of them will work.
Okay. And then it was so. Oh, I see.
So what you're going to end up, for example, the resulting matrix, the solution is going to be 2, 25, 16. The diagonal will be 18.
Okay.
Because in this one, you have some fractions you have to clear.
Oh.
And if you have fractions, you can do math on the matrix. Let's see, what's the easiest way to do this? Okay, so we have an answer. So you can just go times 5.
Oh.
And that's how you clear the fractions.
Okay.
Find out
The common denominator between all of them.
Yeah. And depending on how you have it set up, if you have it set up as a decimal, you still have to clear it.
Okay.
Because decimal is a fraction too. So, and that's basically it. It's a lot of times in linear algebra, they'll use balancing equations as an example.
Mhm.
And but when you look at the extra credit ones I gave you, the second one will take you 30 seconds.
Yeah.
And probably longer because you're not used to setting these up, but
I'll practice.
putting in the matrix, that's what takes all the time. But the concept is really easy.
It seems.
It's just a system of equations that matrices using RREF now allows you to do really fast.
Mhm.
And it's set up on your calculator already.
So you just have to make sure that you're plugging them in correctly, because it seems like it can go wrong.
Yeah. And putting them in is a pain because you got to go put the number in, hit enter, and then it jumps to the next one. So if you forget to push enter, your matrix is wrong.
And then you have to restart.
Yeah. Yeah. So that's the only tricky part is making sure your matrix is valid.
And then on the exam, would you recommend matrix or would you guess and estimate?
On the exam, I'm not going to have any hard balancing equations because the problem, when I give you a stoichiometry problem, if you can't balance the equation, you can't do the problem.
Yeah.
So I'll never know if you know how to do it or not. So I always give you a simple equation to make sure everyone can balance it.
And then are we given like so I walked in late, but are we given like the formula to balance prior to like that question? So it'd
Yeah,
be like
for
this
first
is
test, I'll give you the unbalanced equation. Is that what you
Okay.
mean?
Yeah.
And what the methane is. You know.
Uh,
But as we get into the semester, it'll be less and less of that.
and then for the pre-lab in chapter 5, like the net balancing equations, will that be on the exam or is
No.
that going to be later
That is unit 3.
on? Okay.
I mean, everyone in the department says we moved chapter 5 way out,
Yeah.
and yet the lab director puts that lab
With like what?
after chapter 4.
Yeah.
Exactly. It's way up there. Because it talks about oxidation reduction, all that stuff. We don't cover any of that. That's what I'm saying. Just do the lab, put in the data.
Yeah. And then come back to it later.
Yeah. Yeah, because I was going, what are we going to do? You know, I could spend like 3 lectures on talking about that lab, you know, and then we get behind where I'd have to, anyway.
It's a lot of
Yeah,
reconfiguration.
I decided to do this.
Thank you.
Sure.